Alright, so let's get to another problem solved by Klepner and Kolenkov, and this is on page 264 of the first edition. Page 264, first edition, and the problem is example number 6.15. This is truly a beautiful example, and it's very easy to imagine what's happening, and to be able to say that we're going to predict what's going to happen is a very good feeling. And once again, we fix the coordinate system. So this is z and x and y, and once again we have a disk, and this time it's on ice. Okay, the disk is on a surface which is ice, and the author says that you can assume there's no friction. And now what next? So there is the standard information, mass, radius, okay, and the now here's a variation to the problem. You should imagine that there is a tape wound around the desk, and this enables you to apply a force in this direction equal to F, right? And that's it. Okay, so the question is very interesting. What's going to happen? What's going to happen? Now, it so happens that we have all the information and all the equations to predict what's going to happen, and that's the good feeling that I was going to talk about. What does one do? Well, let's go through all the steps. Let's draw the free body diagram. So, what are the external forces on this object? So, there is gravity equal to mg. Then there is a normal force equal to N, and there is this force applied by somebody along this direction with the help of the tape, and there is no friction, so because we are on ice. But we have all the information we want, and the first thing to do is use the equations we have. So before that, I would like to point out that the author, to consolidate the concepts that we have studied, solves it by method 1 and a so-called method 2, just to tell you that the formulae of method 1 are coming from the law. So what are the formulae that are used in method 1? And then we'll get back to method 2. That is, the force external on the system is equal to mass into acceleration of the center of mass. So why not predict this a priori? That's the first equation. And the second equation is tau cm is equal to ICM alpha, and this will predict the rotation about the center of mass. So we can predict this and we can predict this, and that's the end of the problem. Do we get the same answer when we apply something called method 2? And what exactly is method 2? I'll just mention it. Method 2 insists on starting from the base law, which is the torque is equal to dl by dt, in this case dlz by dt, and tau z. Both tau z and lz are calculated with respect to this origin. Now this is the thing that we need to consolidate in our minds. You must calculate both tau and L with respect to the same fixed coordinate system. In this case, this is the fixed coordinate system, and that's the origin. Okay, so let's get back to what are the predictions of method 1. And there is no reason for us to doubt these equations. So all we need then is our ability to calculate tau about the center of mass and the force external, and this is facilitated by our ability to draw the free body diagram, of which we are reasonably confident. So let's get back to method 1. So I'll try to write down what are the predictions of method 1 with respect to this observer. This observer who is watching the phenomena, and from this coordinate system 0 x y is going to predict based on the two equations, which are our two formulae, and for which he needs the free body diagram. And watch that all the these two external forces are passing through the center, okay, thanks to the geometry, but there is an additional force which is equal to F in this direction. Okay, so let me get done with the first part, which is the force external is equal to mass into acceleration of the center of mass, which is going to be in the object does not move in the y direction, so we can conclude that n equals to mg. Okay, and the in the x direction, F is the only force in the x direction, is equal to mass into acceleration in the x direction, and this implies F, which is given in this problem by the way, divided by m is equal to acceleration of the center of mass. Done. So already we have predicted what is the acceleration of the center of mass. It seems to be a constant. Now next we use the equation tau cm z is equal to ICM, which by the way we have already done in the previous problem, mr square by 2, where r is the radius of this disk and m is the mass of this disk, into alpha. Now this part of the calculation is very easy. Remember that it is with respect to the center of mass, and the observer is now traveling with the center of mass. He observes pure rotation about the center of mass, and you can see that n and mg are both passing through the center of mass, so they have no torque, and the only torque is, if I can write it as minus Fr. Okay, and the minus sign is because, oh wait a minute, sorry, it's in the anti-clockwise direction, so with respect to the center of mass it's in the anti-clockwise direction, so that gets a positive sign. So this is by the way tau z about the center of mass, and now this according to the law is equal to mr square by 2 into alpha, and now alpha is the only unknown, and I get the answer as 2f by mr. Okay, and it's in the anti-clockwise direction. So these are the two answers. So we can predict both the rotational, what happens to the rotation, and what happens to the motion of the center of mass. Now let me just check that the answer is correct. Oh wait a minute, yo, I have some mistake. I'm sorry, can we just check please what mistake I've done? I'm a little surprised that my answer is wrong. Whoa, what is the mistake I've done? Just give me a second. Alpha is I0. Okay. Then discuss FB by I0, FR by I0. Okay. All right. I think this could be. I'm not sure. FR by I0. Okay, so I'm sorry. There seems to be some confusion in the book. So he just calls this as I0. I'm sorry, I0, and in which case then alpha is equal to FR by I0. This looks okay. I'm sorry, this looks okay. He does get FR by I0, so we are okay. Okay, so now let me so let's remember the answer now in this form. FR by I0. Okay, he just doesn't use MR square by 2, he just calls it I0 for whatever reason, so let's not worry about it. Now we have to get to the second method. The second method, obviously the point is to show that you will get the same answer, but it will just improve your ability to handle the formulae that we have. So let's get on with it. Now, an important idea is made more strong in your minds with this example solved by the second method, which is that he now makes use of this origin, and then he freezes time, and he has all the forces which are of course required. I'm just being a little sloppy, but I need to get on with it. Now the first problem is, what is the torque about this origin? Okay, so now the point is that the torque due to n is in the anti-clockwise direction is equal to, if you want, n times this distance, whatever it is. Let's call it something, doesn't matter, it's x in the anti-clockwise direction. But in the clockwise direction you have mgx as the torque about this origin. Should I write it? So tau z is equal to nx negative plus mgx positive. Now these two are equal, and one of them is negative and one of them is positive. The reason is n equal to mg, so they cancel. Plus the torque due to F. Now very important for you to realize this. Lots of times you're going to have this kind of situation. Notice that F passes through the origin. Okay, we are trying to, okay, I just want to highlight this. We're calculating the torque with respect to this origin. Okay, it's very important to do both torque and Lz with respect to the same origin. I'm trying to stick to this origin, and I'm noticing that, and this is a very important observation, it's worth slowing down here. F, the line of action of F is through the origin, which was not the case for n and mg, but then they cancelled out due to one is negative and one is positive and equal. Now plus F into 0, that is the perpendicular distance from the axis is 0, and the torque about this origin for F is 0. Okay, so 0. So the total torque is 0 at that instant of time. The total torque, in fact at every instant of time, the torque about the origin for this problem is 0. So the next question is, what is Lz? Okay, so again we'll stick to the formulae. Lz is equal to, let's see, let's say that the velocity of this at that instant is vcm. Then Lz, we have the formula for that, so let me write it. With respect to the same origin, is equal to rcm cross mvcm. Now what is rcm? We have done this before, so we should be comfortable with this. This is rcm, okay, cross mvcm plus icm into omega at that instant of time, at that frozen instant of time. Now we've done this calculation before, so let's simply write it as minus m vcm r and plus ICM omega t. Okay, so let's continue with this. Right, so this is your LZ. So can I just write this again in the next page? So I have two two carryovers from the previous page. Tau z is always 0, and LZ happens to be minus R M VCM plus ICM omega at that instant. Now, what's the law? The law says that tau z is equal to 0 is equal to dLz by dt, which means that dLz by dt is equal to 0. So since we have L, let's calculate dLz by dt, which is equal to minus R M ACM plus ICM alpha t, and this means that alpha t is equal to MR ACM, but ACM is equal to F by M. Whoa, not too bad. And one second, I forgotten ICM, sorry, ICM alpha, and so divided by ICM, and so this is equal to FR by ICM, and I'm definitely relieved to get the same answer again. And this is exactly what the author is trying to say, that the formula that you have used in the previous so-called method 1 are nothing but coming from the law, which is that tau z is dLz by dt. And just to consolidate this idea, he does method 2, where he directly uses the law and calculates tau separately and LZ separately, and then uses the law. What is the law? The law is here, that tau z is equal to dLz by dt, and when he uses the law and uses a little bit of differentiation, he gets the same answer for alpha, which is FR by I0 or whatever he calls it. And now all the formulae that we have encountered, we've used it now, and they are also matching. So it's time to see what the author has in store for us in the third problem in the book. That'll be my next lesson. Till then, goodbye.